Hi, everyone. Welcome back. So we had a couple of great talks this morning about novel method and integration. And together with Marissa, I'll be convening this session on geomorphology, all things sediments. So let's hope bed levels move up and down. And the first speaker of our session is going to be Mead Allison, a professor at Tulane University specializing in deltas and carbon and sediment transport.
God, don't tell folks I'm a carbon expert. I'm not a
just for these days.
I'm not a carbon expert. I have worked with some really good carbon experts over the years. So, okay, sounds good. Thank you, Julia. So I thought, since I'm not a carbon expert, but to me, DOC is a transport of water through lowland river and coastal systems, and POC is a transport of sediment, I would focus on something talking about the lower part of river systems. And Nick kind of alluded to this earlier in the Amazon, that there's this massive amount of carbon processing that goes on in that system. And so I want to go through a few mechanisms that I think are understudied, that as you look at sort of what the next generation of research may be, I think these are the kind of things that are really interesting. And the biggest question is, we know these processes are happening, but are they really important volumetrically in terms of the carbon budget? And so I'm going to leave you with that thought, and I'm not going to answer that question in this talk. So again, source to sink, POC, DOC sources, there are lots of different sources coming from the basin. And then there is an export of that material to the shelf through deltaic or non-deltaic environments. Again, lots of different mechanisms at work. And so as you look into the past, right, if water is an analog for DOC, there's lots of changes historically, what's coming from drainage basins that potentially affect that source of carbon to the shelf. We've seen these familiar figures in sediment, and each river basin has had a very complex history of a combination of land use change, engineering, and climate change in the past that has generated a major change in sediment flux and potentially a change then in carbon fluxes as well. Then as you look into the future, all the models are suggesting, this is just one example, that global temperatures as they go up will mean global precipitation and catchments will go up, which means river discharges to oceans and total sediment fluxes are likely to be on the rise. And hence, fluxes of DOC and POC will increase, right? I think we all sort of agree that's common. So the summary of this is that changes in the Anthropocene in land use, engineering, and climate change have been critical both historically and seem to be critical in the modeling in the future for how big that arrow is going from catchment, source to sink, whatever you want to call it. So I want to have a thought question, which is to say, if you had a sentinel station and could monitor everything with respect to carbon flux at the land-ocean interface of a river, would the changing signal through time reflect only the variability in the basin source? And I would argue the answer is no, and probably that's the case. But again, there's a whole set of processes that go on in the lowland part of river channel systems that modulate. That's why I called this talk the modulator. They can provide additional sources of sediment and carbon. They can remineralize carbon, transform the nature of carbon, and importantly, they can also affect the timing of the release to the oceans, seasonally. So I'm talking when it's released with respect to energy characteristics on the shelf, for instance, and so forth. And so that's what I really want to focus on today is outlining some of these mechanisms. So the title of my talk was about the Mississippi and the Mekong and other systems, and I've had the opportunity to work in a lot of systems around the globe. Probably would have ended up in an hour-and-a-half talk if I'd followed that. So I'm going to really talk about the Mississippi, allude to the Mekong a little bit, but my point with the other systems is that hopefully these processes are to some degree universal in river systems. And so what goes on is, if we use an example of the Mississippi, could be relevant in other systems around the globe. Oops, come on. Okay, so what do we mean by the lowland part of a river system? And I'm going to use the sort of fluvial terminology here, right? The lowland part of the Mississippi system extends all the way well up above Louisiana, somewhere in the vicinity of Vicksburg, Mississippi, 700 kilometers from head of passes in the river mouth. This is a paper just talking about the backwater reach of the Mississippi, a fluvial term that simply says, you know, during low discharge, we have this concave water surface elevation slope. This is a low discharge in the Mississippi River. And what we're seeing is the influence of the ocean affecting the unidirectional transport of the river, slowing, and in lower reaches, we start to see tidal and estuarine processes as well. At higher discharges, this kind of thing is reduced. The water surface elevation is more controlled by the river. And that's very important from a standpoint of the flux of particularly sediment and any carbon that's associated with the sediment through the system. Another thing that's key in this area, that 730 kilometer point, you notice is the point where the channel bed thalweg rises to above sea level, right? So again, that gives you a sense of why we're in this backwater reach. So this is the part of the system I'm going to concentrate on. And again, it isn't a singular system, right? You can envision a system that the upper part of the backwater reach tends to be non-tidal, reduced energies, but no tidal perturbations. Then we go into a reach as we approach the coastal ocean of tides in the Mississippi, because the Gulf of Mexico is so low, we never reach or tidal perturbations in the Gulf of Mexico are so small, we never reach a reversing tidal stage down here in the system. So we don't have the yellow, and then at low discharge, we have penetration of estuarine conditions into the river mouth, right? So we have a series of different sub-environments that are potentially important for this total transport of carbon through the system. The Mekong, I said I'd mention briefly, all rivers have this kind of backwater reach. Nick sort of mentioned the tidal affected Amazon earlier, and that's 1,000 kilometer plus, just the tidal reach of it. The Mekong channel, this is some work I was involved in a few years ago. This is the channel thalweg moving down through the system. The difference here is that we have a very high tidal range and much more tidal influence in this backwater reach of the system, to the point which we see a non-tidal well up the system. Then we see a unidirectional tide where it's moderated potentially or augmented by the tidal flux. Then we have a large area reversing current energies in the river channel before moving into estuarine conditions again. In this case, during high flow, we see strong stratification in the narrow channel, and we see a salt wedge. In lower flows, lower river flows, we see more mixing, vertical mixing from the tides, and so we're more in a partially mixed estuarine condition. So even over the standpoint of just a short period, and this is just sort of showing the same thing between low flow, this different zonation, and depending on what system you're in, and then you move to high flow and the shift of these things spatially in the system. So again, what lower river dynamic mechanisms have been identified that potentially impact the throughput of carbon to the ocean is what I'm going to focus on in the Mississippi example. So to start out, here's a study we did above Baton Rouge in the area of St. Francisville, Louisiana, up to where the Atchafalaya leaves the channel along that pathway. And there's a major reduction of sediment load, suspended sediment load from the USGS stations measured in this reach between the Old River passage into the Atchafalaya and down to Baton Rouge, which is where we are today. And it's about 34% of the fines. This is averaged over multiple years, and 40% of the annual sand load. And the question is, why are we losing this much sediment in this relatively short reach of the backwater channel? And we think there are two things going on here. One of them is actual channel storage. Now, remember, when you take 30% of, as much as 30% of the water off the river into the Atchafalaya, you lose a lot of stream power and the capacity to transport sediment. And therefore, you should see a depositional signal in the river channel below that, primarily of sand-sized material. And this is just showing some work that David Biedenhard and I and a number of folks did, showing that from the station at Red River Landing, which is just below the old river Atchafalaya offtake. And this is, if you've never seen a specific gauge record, basically you're just saying at a given discharge, and I'm sorry, these discharges are in US numbers, cubic feet per second, because this was an Army Corps publication. And but anyway, what you'll see is if you follow a given discharge, this is a moderately low Mississippi River discharge, 400,000 CFS, and you look at the river stage and individual USGS measurements of discharge, you see a rising gauge. In other words, at a given discharge, the stage rises through time, and that's an indication that the bed is aggrading, and therefore the water surface elevation is increasing at a given discharge. So this is sort of indirect evidence that we're seeing aggradation on the bed. I just had a student, Christina Legas, finish a master's thesis working up in this reach of the river. And this image actually shows in cyan the degree of flooding at high discharge. And the other interesting thing about this reach is that it does not have tight guide levees, unlike most of the Mississippi River, because there are natural high grounds, tertiary high grounds over here, and Pleistocene high grounds. They never bothered to build a levee over here. And so this is sort of a natural Mississippi floodplain situation in this. This is Cat Island National Wildlife Refuge, by the way, home of the world's largest cypress tree, if you've ever get a chance to visit. And anyway, this is sort of in a big flood year, how much inundation occurs on a day perspective in a low flood year. You can see this bend in the river is still enormously active in terms of overbank flooding. And this results in a massive amount of sedimentation in the system, floodplain sedimentation. This is sort of a combination of feldspar plots and beryllium activity measuring in 3 different flood years. And you can see this massive amount of sedimentation on the natural levee, and this is a natural levee, and then a rapid drop off into the back swamp of the area. So overall, without going into the details of the sediment budgeting, about half of the sediment we can account for is, sorry, this is the next topic, about half of the sediment in that loss below Old River to Baton Rouge is channel storage, primarily sand. But one of the points I'm going to make is that in the Mississippi and a lot of other systems, we think of sand as being sort of a very low organic content. There's actually a lot of woody, large particle woody organic matter, what we call coffee grounds in this local system, to give you a feel of what it looks like, that behaves hydrodynamically like sand-sized particles. And so if you're storing sand out there, you're potentially storing woody organic matter as well. And then both fines and coarse material are going into the floodplain, primarily sand here on the natural levee, and then fines in the back swamp. So again, in systems that aren't tightly levied around the globe, you are going to still see a tremendous amount of a loss term into the system occurring. Okay, moving on to another mechanism. This is a really cool survey my Army Corps colleagues did. They did a Lagrangian boat survey. They used multiple boats and tracked a single water mass down through the backwater system at low and high discharge in 2012 and 2013. These are the water surface elevations at the low discharge and the high discharge, again, showing the backwater reach characteristics. These are the mean cross-sectionally average water column velocities, and you see how dramatic the drop-off is in water column velocity in the Mississippi River through the backwater reach at low discharge, and how relatively invariant it is and much more energetic at high discharge. So the potential is there for a massive storage of particles and remobilization. And this is a very busy plot, so I'm not going to go through all of it. But the upper two plots, these are the two surveys from in terms of suspended sediments that was measured at each one of these cross sections in a Lagrangian way. And you see that the suspended flux at the low discharge survey is dropping dramatically. That means all that sediment is raining out onto the bed, including fines. Wash load is raining out on the bed. This is a breakdown of the grain size. At high discharge, you can see that there is a relatively small reduction in sediment flux. And so that material is throughput directly to the ocean during that period. So the implication also is during the rising limb of discharge, all that material that is stored on the bed in the backwater reach for a period of months is remobilized over a period of days to several weeks and flushed to the shelf. So you're affecting both the flux and what might happen to the material on the bed in terms of carbon transformation while it's cooking on the bed of the Mississippi River under highly oxygenated conditions. And also the timing of then when it augments in the rising limb, new material coming down from the basin. And we see this in the estuarine reach as well. John Galler did a PhD with me a long time ago. And so there's this massive amount of storage down in the estuarine reach, classic estuarine turbidity maximum processes up to, these are several meters of fines deposited on the bed in the Thalweg of the channel during one of these low discharge events. And again, that material is remobilized in the rising limb. Oops, went the wrong way. Sorry. I knew I'd do that at least once. This is an interesting idea that I want to just leave out there. And we've never looked at this from the carbon point of view. Most of the lower Mississippi, as you see in this multi-beam image, is made up of these lateral sandbars. So the Thalweg of the channel is crisscrossing across these sandbars. And you can see some of the large bed forms on these sandbars, even though I didn't. This is a paper we wrote a number of years ago, Mike Ramirez, that was about what goes on the surface of one of these sandbars as discharge goes up. You can see the bed forms are getting larger. The bed load transport flux is also going up. And then this is cross-sectional ADCP measurements of the backscatter that we've used real samples to calibrate. And this is sand in suspension. As we have rising discharge, there's this massive amount of resuspension over the bar that's caused by larger bed forms, more turbulence. You're kicking material off the bed forms and up into the lower part of the water column. So that has me thinking if there's a lot of woody organic matter in these sediments, there's this massive amount of processing that goes on. I'm seeing Bob here, I think bed incinerator, right? If you're in highly oxygenated conditions and you're taking this sand and associated organic material and throwing it into the water column at a very high frequency and then redepositing it, moving on to the next bar, there's something like 40 of these bars from New Orleans down to the mouth of the river. This is potentially a huge way you could consume carbon. We don't know, but I know a lot about how the sediment dynamics works in this. What we really need to know is what impact this might have on carbon. This is just, again, how incredibly dynamic these bars are. This is something we did for the mid-Barataria, or sorry, the mid-Breton potential diversion. We had an incredibly dense sampling network where we calculated suspended sand fluxes, and you can see they vary tremendously across the surface of this bar by a factor of 2 or 3. As the dynamics, you can see sort of like net aggradation on the surface of the bar, and then at the toe of the bar, these things lift off again as we move down to the next bar. So there's an incredible amount of dynamics going on in these things that none of this data is published because it was done for the state of Louisiana. Oops, I did it again. Okay. This is another thing I would like to leave out there as a possible thought. This is some work that Tom Bianchi and I did a long time ago, and some later work that Jeff Nitrower, when he was a student of mine, and later did. And one of the interesting things is that a lot of the lower riverbed is actually relic strata exposed. especially in these bins. And there's several types along the sidewalls and on the channel floor where if you core this material, you get into the underlying deltaic strata, right? And when you get up to New Orleans, in these deep holes, you're actually picking up Pleistocene material. It's deep enough. And so as that material erodes, that is injected relic carbon into the system, and which is a really interesting potential source. And so I just want to think about the idea that now that we've straitjacketed this river and many other rivers around the globe, we've locked these rivers into place. And so these high energy zones potentially are getting deeper, right? We're carving away because the rivers are no longer allowed with the revetments to migrate laterally. They're incising deeper. So another potential impact of human engineering on these systems is to maybe increase the source of this relic carbon in the backwater reach that's injected into the overall transport stream. Okay, so this is really my last slide, and I kind of hurried through this, but I did want to talk about each one of these things just briefly to kind of say what might they be, because I ran through them pretty quickly. So distributary natural and anthropogenic water loss drives channel bed interannual storage of coarse POC. In other words, an anthropogenic distributary would be something like a river diversion, right? If you create a river diversion, you reduce the stream power. We've seen it in places where we have temporary things like the Bonnie Carey spillway here. We'll see rapid deposition when the spillway is open on the channel floor. And then when they close the spillway, that material is remobilized. Well, if you have a permanent distributary, presumably you're going to have a stream power loss and you're going to have a storage of coarse material on the bed relatively permanent. And that could be thought of as a carbon sink if there's large particle woody material associated with it. Overbanking in non-levied reaches drives POC storage and DOC transformation when you have that material. Now, the really interesting thing about what we've done to rivers is that we used to have a lot of lateral migration, and so we deposited that stuff into floodplains, and then it got recycled as rivers migrated laterally. Well, the Mississippi, like a lot of other rivers, are revetted now, and that's no longer allowed to happen. So these become sort of burial places now. Like Cat Island is now a place where you're constantly adding material, but you can't envision that meander eroding that material out in the coming centuries. Backwater reach stream power loss causes low discharge bed storage of fines, including degraded soil POC and organic mineral aggregates. We showed there's this dramatic deposition of material in the backwater reach during low discharge periods, and then that material is remobilized during high discharge. That's not a permanent term, but while that material is cooking on the bottom for a period of time, you could transform the carbon, and you're also the timing of export then is strongly controlled, is impacted by this as well. Same thing's going on in the estuarine reach, as we said. The processing on sandbars is a lost term potentially. Channel hardening leads to increased excavation of relic carbon. I didn't talk about the Mekong example, but a lot of rivers were also sand mining like crazy as well. And so that is a lost term, and a true anthropogenic lost term. We're putting it on a barge and we're taking it for construction aggregate, then that's part of the budget. So I just leave you with this thought that we're starting to see lots of different mechanisms in this backwater reach. The question is, volumetrically, are they really critical in terms of the overall carbon budget of what transitions from source to sink? And that's all I have. Thank you.